Deep inside the Great Pyramid, a robotic camera is crawling through a perfectly straight, pitch-black stone shaft. It navigates this claustrophobic 4,500-year-old tunnel until it hits a dead end, a stone slab blocking its path. Before we can discover what lies behind that ancient seal, we have to solve a physical problem. How did that slab and the mountain of stone surrounding it get there in the first place? This chart shows the total mass of the Great Pyramid compared to modern structures. Its base spans 13 acres, constructed from 2.3 million blocks. At 6 million tons, it packs the weight of 12 Burj Khalifa towers into a single footprint. The structure has survived thousands of years of earthquakes and severe storms without shifting a single inch. These ancient builders operated without magnetic compasses, laser levels, diamond-tipped drills, or heavy machinery. The Great Pyramid stands as a contradiction of human history, a flawlessly precise structure achieved entirely with primitive tools. The primary rule of constructing any megastructure is simple. To build 480 feet into the sky, you must start with a foundation that is perfectly flat and perfectly aligned. The engineers faced a difficult orientation challenge. They needed to align that 13-acre base to true north, south, east, and west without a compass. True north is the fixed geographic North Pole, distinct from the shifting magnetic pole that compasses point to. They solved this using the stars. By tracking the circular movement of specific polar stars in the night sky, architects mapped Earth's true poles. Bisecting that arc creates a geometric line pointing to true north, allowing them to mark the exact corners of the pyramid. Next came the leveling challenge. They had to flatten 13 acres of uneven bedrock to a microscopic degree of accuracy. The prevailing theory points to a water trench system. Workers carved a grid of connected channels into the bedrock and filled them with water. Gravity forced the water into a perfectly horizontal plane. By measuring from this water surface down to the rock, engineers identified high spots. Laborers chipped those points away until the 13-acre site matched the water's level. To perform a final quality check, they used an A-frame plumb bob. This is a wooden triangle with a string and stone weight suspended from the top. When placed on the bedrock, if the string aligns with the center mark, the ground is flat. Through the observation of stellar orbits and the physics of resting water, ancient engineers achieved a level of foundational precision that matches modern optical instruments. With the foundation set, the architects turned to the logistics of carving millions of limestone blocks from the earth. Pure copper is too soft to cut rock. To solve this, engineers relied on a metallurgical innovation. They chemically doped their copper with arsenic. Doping is the intentional addition of impurities to alter a metal's properties. In this case, the arsenic bonded with the copper to forge hardened chisels. But a different material was used deep inside the pyramid. The inner chambers and corridors were built from granite, the second hardest stone on Earth. Slicing through solid granite with such clean precision usually requires modern motorized grinders. They used an abrasive sawing technique. Engineers pulled long, toothless copper saws back and forth while continuously pouring loose sand and gravel into the cut. The hard quartz grains in the sand acted as the actual grinding teeth. It took teams up to 4 months of continuous sawing just to cut a single block of granite. Extreme patience, combined with the raw friction of sand, solved a material density problem that today involves industrial diamond-tipped machinery. Once cut, the problem shifted to transportation. The high-quality white limestone for the outer casing was quarried in Tura, 250 kilometers away from Giza. Individual blocks weighed up to 50 tons, the equivalent of 3 passenger buses. To move that kind of mass, ancient engineers leveraged the Nile River, establishing an aquatic supply chain. The manpower required was significant. Coordinated groups of up to 500 men worked simultaneously to load and unload a single 50-ton block onto wooden barges. Then came the final vertical challenge. They had to lift 6 million tons of rock up 480 feet into the air without cranes or pulleys. Engineering theory suggests the use of winding zigzag or spiral earthen ramps built around the perimeter of the pyramid to drag the stones upward as the structure grew. The true technology behind the pyramid's construction was logistical organization. synchronizing thousands of skilled laborers, fleets of river transport boats, and massive stone hauling ramps into a single assembly line. This structure represents a physical reality of stacked stone and human labor, independent of myths or external intervention. It stands as a record of hyper-organized labor and the application of elemental physics. When you look at the pyramid, you are looking at the result of stars, water, sand, and human effort. We have decoded the construction methods, yet the specific purpose of this fortified inner architecture remains unexplained. This brings us back to the robotic camera, currently face-to-face with the drilled stone slab in the darkness. What did the camera's lens capture when it finally breached that seal? Watch part 2 to uncover the truth.